So last time we were talking about the Doppler effect, and at the end of last time we talked a little bit about how musical instruments work. So I just want to let you guys know that actually I need to update that. After lecture, I'm going to update the lecture 3 notes. There was an example that I should have linked to at the bottom of lecture 3 in the lecture 3 notes last time that I didn't, so I'm going to update it with that link so you can take a look and just get some practice. Today we're going to continue talking about interference effects for sound, and we're going to finally start handling like real world, not quite real world, but we're going to talk about more complicated scenarios. So really, we've been talking. I mean, all of the interference that we've been talking about has been one-dimensional interference. So let's continue talking about 1D phase differences. Remember that the interference, or the result of the interference, whether it's constructive, destructive, or somewhere in the middle, those depended on the phase, at least in one dimension. In 2 dimensions, the interference also depends on distance. In 3 dimensions, it also depends on distance and more than that. But what we can do is we can use what we've learned about one-dimensional phase differences to generalize to more complicated systems. So for example, if we want to model what happens when there are 2 speakers in a room, well, that's kind of tricky. God, I love writing on this tablet so much more. Such a nicer tablet. So for example, if you have your room, this is say a top-down view, and you have a speaker over here and a speaker over here. Now let me make them different colors. Then, how do I make this less thick? There we go. Then this speaker will emit sound waves in a spherical shape that will fill the room, and there'd be bounces, but assuming that there are no bounces off of walls, this is roughly what the pattern would look like. And then you'd have another speaker, say over here, which would emit its own spherical pattern of sound waves. And they're spherical because it's 2-dimensional and they're coming from a point source. And so the question is if these waves that are produced have the same wavelength, the same frequency. I mean, if they have the same wavelength, then they have the same frequency. They're traveling through the same medium, they're the same type of wave, they're both sound waves. So the question is in this room, what type of interference do you get? Do you get constructive interference? Oops. Do you get constructive, destructive interference, and where? I.e., so what it would look like in this room is there would be some regions where there are quote unquote dead zones, regions where you'd have destructive interference, where the peaks and align with troughs. And the reason this can happen, regardless of direction, is because regardless of like direction from the sound waves, the reason that can happen is because the pressure or the density, the pressure doesn't have a directionality to it. So if one wave's traveling one way and another wave's traveling another way, but the peak of one wave is the trough of the other, then you'll get interference even though they're traveling in opposite directions. Just wanted to get that aside. But the point is there will be interference everywhere in this room. And the question is, what are they? The dead zones would be things like destructive interference, where you can't hear anything because both the sound waves are exactly canceling out at that region. And then there would be regions where the sound waves are amplifying each other because their peaks line up with each other, and you'd get constructive interference. In that case, it would sound extra loud. So the only way, as I said, the only way to get constructive or destructive interference is for the peaks and troughs of the waves to match up. So for what follows, we are going to assume the same wavelength and period and frequency. I mean, all of these things are related. If they're the same wavelength, then they're the same period and so on. But we're just going to assume that these are the same waves being generated, perhaps at different phases, perhaps turned on at different times, but they're otherwise like the same type of wave. They have the same wavelength, the same frequency, and so on. Just so then we can actually try to understand the interference patterns for this simple case. And so to determine whether or not there's constructive and destructive interference and where those are, we're going to consider the overall phases. And we're going to do this in one dimension because really, it doesn't actually matter. Like if we're looking at a point here, all we need to do is compare the phases after the wave has traveled this far for that amount of time in both cases. And then if the phases match, then you'd get constructive interference. If the phases don't match, you get destructive, or if they anti-match, then you get destructive interference. And then everything in between will occur. Now, you might say, well, wait a minute. Isn't it true that when two waves travel different distances, their amplitudes will be different? How could you get destructive interference where you get zero sound? Well, I mean, you'd be right. That is true. The amplitudes will be different. For the most part, we're going to assume that for what follows, we're going to assume that the amplitudes stay the same. And the reason we're doing that is because the change in amplitude doesn't actually affect the type of interference. It just affects the magnitude of the interference. So rather than having true dead zones, if one of the waves is significantly less intense than the other wave due to distance traveled, like for example, if we were interested in interference occurring here, one wave has traveled significantly further. While it is true that the interference wouldn't be complete if you had a dead zone there, say, you would still have destructive interference. So it would still be quieter there than in all surrounding areas, just because the peaks and the troughs still anti-align. It's just they wouldn't completely cancel out because they don't have the same magnitude. But we can still study this. And so we're just going to disregard the discussion of amplitude for now. We're going to study just the effect on phase. And then later, if we wanted to, which we won't, but we could reintroduce this notion or reintroduce amplitude and see how that affects things. And hint, it won't really affect things. So we're going to consider the overall one-dimensional phase because if we're just looking at a particular position in the room, we can treat these as just waves traveling in one dimension because we're disregarding how amplitude changes. Phase still total phase still changes in the same way. If you travel a distance, then your phase increases by 2 pi x over lambda. If you wait for a duration, your phase increases by 2 pi ft, and so on. So all of those things are still true. We can just treat these as if they're one-dimensional waves going towards the point of interest. So we're going to consider these as 1D waves. All that does is it gets rid of the amplitude change. Everything else stays the same. So you might remember from Friday, the total phase difference is just the total phase of wave 2 minus the total phase of wave 1, which we can compute. Remember the total phase being the stuff inside the cosine. So in this case, this would be 2 pi x2 over lambda plus 2 pi t, sorry, I'm using this convention, 2 pi f t2 plus phi 2 minus 2 pi x1 over lambda plus 2 pi f t1 plus phi 1. Now, so here, x doesn't mean motion along the x coordinate, right? What x means is the distance traveled from the source. Now, before, when the two sources were aligned, it was kind of just a straight distance. But now perhaps you can actually see why x1 and x2 might be different. For a given position, say xy, x2 will be a different number than x1, even if say they're turned on at the same place, or even if they are aligned with each other, right? If this green one was instead here, the x2 would be the distance traveled, not just the motion in the x direction. Right, so we can simplify this equation a little bit. This is 2 pi x2 minus x1 divided by lambda plus 2 pi f t2 minus t1 plus phi 2 minus phi 1. This is equal to 2 pi delta x divided by lambda plus 2 pi f delta t plus delta little phi. So here now we can just look at these quantities again. So just as normal, lambda is wavelength, f is frequency. These are the same for both. But now we can look at what the other quantities mean. Delta x here is the difference. Say they were turned on at different times, right? Then the amount of time that one of them has been going would be different from the amount of time that the other one would have been going. So T2 and T1 would be different. We will go into that, by the way. So here, delta x represents the difference in distance that they've traveled. So depending on where you put your point of interest that you're studying, that delta x will be different. Similarly, like I just said, delta t represents the difference in time that the two wave sources have been active. And the reason for that is that if you wait half a period, the wave inverts, right? So the wave goes up and then it goes down. So like if one of the waves was, or one of the sources was turned on half a period earlier, sorry, if one of the sources was turned on half a period earlier, then it would be like it was starting with a different phase once the other wave was turned on. Of course, we're only interested in the times when they're both already on. So we don't investigate cases where one wave has gotten to a point, but the other wave hasn't yet. We're interested in a steady state where both waves have had time to get there, but they've been on for different amounts of time. And then finally, delta phi, this is just a measure of how different they started out as. So if one of them started off at a peak and the other one started off, why can't I write a phi? If one of them started off as a peak and one of them started off at a trough, then they could potentially interfere in a different way than if they both started off at a peak. The delta phi was equal to phi 1 minus phi 2. Yeah, so this doesn't matter. And the reason for this is because the cosine of x, or the cosine of x is equal to cosine of negative x. This is the same thing, doesn't matter. Yeah, so it really doesn't matter here. You could even, yeah, I'll just leave it at that. You can use either one, and it's just because cosine is symmetric, right? Cosine of x equals cosine of negative x. And so long as we use cosines for our wave functions, then it just doesn't matter. Right, so the question then is, how can we use this total phase difference to get just to figure out where we'll have destructive interference and where we will have constructive interference? It turns out it's fairly straightforward. The same is true. It's the same rules that we had for one-dimensional wave interference. And the reason it's the same is because all that matters for constructive or destructive interference is whether the peaks and troughs align or not. And so we still, regardless of whether it's a two-dimensional or three-dimensional wave, we still only care about the total phase difference because that just tells us where the peaks and troughs are. So the total phase difference, or rather it tells us how aligned or anti-aligned the peaks and troughs are. So the total phase difference here, if the total phase difference delta capital phi is pi or 3 pi or 5 pi, etc., then we get destructive interference, just like before. On the other hand, if delta phi is 0 or 2 pi or 4 pi, etc., then we get constructive interference, i.e. we get a loud spot. And otherwise, if delta phi is not some integer multiple of pi, then you just get something in between, i.e. you get slightly louder, slightly quieter, whatever, you just get something else. Right. So the question then is how can we, what can affect delta phi? Well, we've already talked about this. The basic gist is that they could travel different distances. That's probably the most basic. If they traveled different distances, but they were on for the same amount of time and they started off with the same phase, then these guys would be 0, and delta x would be the only thing that's affecting the interference. And so you could figure out, well, when is 2 pi delta x over lambda equal to pi or equal to 2 pi or whatever? You could use that to figure out what regions have dead space and which regions aren't, or which regions don't, assuming the speakers were turned on at the same time and they had the same input phase. Likewise, they could travel for different durations, meaning that they've been on for different amounts of time. Actually, let me write that a different way. Let me just put emitting for different amounts of time. And the reason I'm writing it this way, by the way, is because the amount of time that it takes to get from point A to point B doesn't matter in the phase. Like that's not something you account for. So you wouldn't say that because something is further away from one speaker than it is from the other, that it takes longer to get there. That's not what we're talking about. We're talking about how long has the wave actually been going. That's the important thing, not how long it took to get from the speaker to the point or to the location of interest. So we're really interested in a property of the speaker, not a property at the location. They could have also started out of phase, meaning that delta little phi could be 0. One may have started out a peak, one may have started off a trough, or it could just be any combination of the above. Right, it could be that they traveled different distances and they were turned on at different times and they had different phases. You could have a whole different combination of things. So we're going to look at each case separately. And what we're going to do is we're going to treat it as if it were one-dimensional just to draw pictures. But again, remember that these are just like, they're just graphical depictions. They're not, it's not an actual representation of reality, right? It's just a way to try to understand what's happening. So we're going to look at each case separately, as I said. And so let's do the first case, that they've traveled different distances. So the speaker assumptions that we're going to assume are that the speakers start in phase, i.e. maybe they have the same input. We're also going to assume that they were turned on at the same time. Say delta t equals 0, or so that delta t equals 0. By the way, if they start in phase, that means that delta little phi is equal to 0. That's why we're doing this. We're going to basically turn on each different way separately. And then let's say that the two speakers are offset by a small distance delta x, meaning that maybe their distance from the point of interest is slightly different. So in this picture, it would look like picking a place, say, oops. Maybe like here. So like the purple one travels a little bit further in this case than the green one. Yeah, there will be a, well, no, the problem on the homework doesn't actually involve this, but it's the problem on the homework is tangentially related. Or wait a minute, is there a problem on the homework like this? There will be a problem on the homework like this. Was that a question or was that a statement or? Yeah, no, there wasn't a problem like this in the homework. Yeah. So the problem on the homework was one-dimensional. This is, but you're right. This is very similar. Right. Sorry, I got off track. Right. So the picture then is something like this. You have one speaker. Say it looks like this. That I'm just going to draw a horizontal line to depict it, oscillating like this. And then you have another speaker that's offset by a little bit. Come on, let me copy this, please. Paste. Oops. So it would be like offset like that, say, for example. And so this distance here, oh, stop pulling up that, please. This distance would be delta x, right? And so in this scenario, they are not actually one right behind the other. On a homework problem, they are one right behind the other. But in this scenario, they're just traveling different distances. We're just depicting them this way because it's easier to visualize. And so in this case, if delta x is equal to lambda over 2, like I've drawn, then we would get destructive interference. And the reason for that is exactly as I've depicted. So look, so if this distance is exactly half a wavelength, that means that by the time this one has lined up with this one, it will have undergone 1/2 of a wavelength. And so it would be at a minimum when the first wave or the top wave is at a maximum. We can see this more explicitly mathematically. In this case, delta phi is equal to 2 pi delta x over lambda, because delta t and delta little pi are 0. And so this would be equal to 2 pi times delta x over lambda. I'm just putting parentheses. And so if delta x is equal to delta or lambda over 2, half a wavelength, then this would be 2 pi times lambda over 2 divided by lambda, which is just 1/2, which is equal to pi. And so as we discussed above, if the total phase is different by pi, then you get destructive interference. So if they're offset by just a little bit, then you can get destructive interference. Now let's look at another set of another case. In this case, we would have that delta x is 0, meaning that the speakers are aligned with each other. We're going to assume that delta little phi is 0, meaning that they start off in phase. But we're going to assume that they were turned on at different times. And everything else is the same. Now, in real life, doing this in a one-dimensional way, this would be impossible because you would have to put your speakers like overlapping each other. But in a two-dimensional case, we can do this fairly easily. Just pick a point that's halfway, or pick a point where they both travel the same distance. In that case, you're good. And feed them the same input so that their phase constant is the same. But then just turn on one of them later. That would do it, right? So this is going to be a little bit harder to draw. So let's say we have speaker 1 and speaker 2. So speaker 1 is going to be turned on half a period later. So at t equals half a period, 1 turns on, and 2 turned on at t equals 0. So at half a period, so at t equals t over 2, 1 is just starting out. So it hasn't, like, it just barely has anything there. But speaker 2 has emitted a little wave, right? Because it's been on for half of a period. And then we can ask what happens at a later time. Speaker 1, speaker 2. So at t equals the full period, at t equals t, oops. Well, the wave 2 will have gone another half a period, so it'll look something like this. And wave 1 has now been on for half a period, so it will look like this, because it has to be identical to the second speaker just turned on half a period later. And so now we see that these two humps destructively interfere. And notice that in this case, speaker 2 has a half period head start. But we only care about the interference once they're both already there. So this is to say that if delta t is equal to the period divided by 2, then we get destructive interference again. And again, we can answer why. Well, delta capital phi, in this case, because all of the other deltas are 0, we have 2 pi f delta t, which is equal to 2 pi delta t over capital T over the period, which is equal to 2 pi. Now here, if delta t is capital T over 2, we have 2 pi times a half, because capital T over 2 divided by capital T is 1/2. And this is equal to pi, which would give us destructive interference. So this is the second way that this could happen. Finally, we can just do the last case, which is relatively easy to understand. It's the case where they are the same distance away. Oops. Oh boy, did my pen stop working? Oh, this is not the time. Oh my God. How about the other pen? Why does this happen? All right, both pens stopped working, which means I'm going to change to a different tablet, which I hate doing, but I have to do this because I forgot this is the reason why I stopped using this good tablet. One moment, technical difficulties, sorry. I don't know if it's like an overheating issue or what, but let me mute myself on this machine while I join the other one. Oh, you know what? Oh, that's terrible. Oh, that's sorry. That's because I double muted. Yeah. So what I'm going to do is I'm going to keep my video up on the other tablet because that still works and it won't stress this computer as much to have my video on this tablet. And then I'll share any GITs that I have to share. I will share from the other tablet as well. I just have to somehow minimize this. How do I get out of? Exit full screen. There we go. Okay. Hopefully you guys can hear something. Actually, you know what? There we go. Oh boy. Where's the volume? All right, how's that? Should be the same video, same audio, but I'm writing from a different tablet. Is that okay? Okay, sorry, I can continue now. Right, so the last case, I hate technical difficulties. Yeah, speaking of audio, no, that's not a bad example. So the last case is one where delta x is 0, delta t is 0, and delta phi is not 0. So this is just the case where they're exactly the same, but they have different phases. So in this case, the picture is relatively simple. Like they're turned on at the same time. That's too big. They're turned on at the same time. They travel the same distance. They just start off out of phase. Maybe one starts off going up and the other one starts off going down. Maybe one of them has a phase of 0 and the other one has a phase of pi. And so if they start off out of phase, by delta phi is pi, then we get, sorry, not 0, delta phi is pi, then we get destructive interference, exactly as may have been predicted, which is just to say that you can get dead spots for a multiple of different reasons if you have two speakers in a room. Now, the most common, by the way, will be the case where you have spatial differences because the speakers are in different places. And in fact, in very special rooms, rooms where the shape of the room is such that you get like reflections in particular ways, you can actually have a single source create dead spots on its own because its reflections off of the walls of the room will produce interference with itself. It'll form like almost like a standing wave, and there will be nodes in some places where the amplitude is always 0. Now, just as an aside, because this will just make things easier, we're not really going to worry about how long speakers have been turned on going forwards. Instead, we're just going to, well, let me write this out. So instead of talking about time differences, we're just going to give them the same stopwatch, i.e., we're going to start time for both of them at the same time, and we're just going to adjust t equals 0 so that the change in time can be absorbed into the phase change. Let me explain. 2 pi delta t times f, rather, sorry. 2 pi f delta t becomes part of delta phi. This is just to say, like, if our old phase was 2 pi delta x over lambda for old total difference in phase plus 2 pi f delta t plus delta phi, we just absorb their difference in times. So we call T1 or T2 equal to, say, T plus let's call it T2 prime. This is like a change of variables plus how do I want to do this? No, we'll call it T2T plus, say, delta T over 2. T2 is the one that's above. Yeah, plus delta T over 2. And we call T1 equal to T minus delta T over 2. And so then, this is just a number now. Delta T is just a number. So delta T is just, I mean, it literally works out to be delta T, but we can absorb this into our delta little phi, 2 pi delta x over lambda plus 2 pi f t minus t, which is, you know, the difference of this part, and then we're going to absorb the second part into delta phi, plus delta phi plus 2 pi f delta t. Basically, we're just going to take what 2 pi f delta t is, and we're just going to call that part of delta phi, rather than worrying. And the reason we do this is just because we only care about what happens when they're both on already anyway. So we can just replace this notion of them being turned on with different times as if they were both turned on at the same time, but one started out however far before the other one. So it's as if it had already been going for a while, but now it just has a different starting phase because it had been going for a while already. It's kind of confusing, but the basic idea is just, you can just swap this notion of being turned on beforehand with starting with a different phase. It's totally equivalent. So this swapping just lets us discuss delta x and delta phi, which is more useful because they're a little bit more tangible things. We don't really care about when things were turned on. We care about like the position and the phases of these things. Okay, so with that in mind, and I can't scroll up to show you. So with that in mind, we now have all the tools to figure out where the dead zones and where the loud zones are. We just figure out what places have delta x's that are the same, or the delta x's that are multiples of the wavelength, or half integer multiples of the wavelength for destructive interference. And if they have different input phases, that will affect it too. So that covers more or less sound waves in like a two-dimensional setting, like in a room. So what about, and I promised I would get there, what about if you have interference where you have different frequencies? right? So far, all of the interference we've talked about is interference between two waves with the same frequency. But like I said, you can have interference with different frequencies because it's still just an area of high pressure and an area of low pressure. And so if you add those two together, you get an area of medium pressure or an area of zero differential pressure. So regardless of the frequency, you'll still have waves adding and subtracting. So we need to worry about that. And so this notion of waves with interfering with different frequency produces something called Beats by Dre. No, it's not sponsored by Beats by Dre. This produces this notion of Beats. And I think Beats is covered in, yeah, it's also in section 2.3. Question, I'm curious as to what happens when there's a complete destructive interference in terms of sound waves. Is there no sound detectable at all? Like, becomes completely silent despite how loud they'd be? Yeah, no, that's exactly what happens. If you've ever been in a room where they're in like a poorly, a poorly designed sound theater or whatever, there will be places where it's extra quiet because, you know, they have a speaker here and a speaker there. It turns out that depending on what sound is being made, the room would be extra quiet. Now, the reason why this doesn't happen all the time is because most sounds, like music or talking or whatever, are composed of a whole bunch of different frequencies added together. And so the location of these dead zones depends on the frequency or the wavelength of the waves that are producing them. And so whereas some of the wavelengths for any given sound might destructively interfere at one region, not all of them will. And so on average, for a whole bunch of different frequencies put together, there won't really be any dead zones. But if you were to just play like a pure sine tone, like a, if you were to just play that sound over speakers, yeah, there would be a place where you just can't hear anything. Now, again, we have two ears. And so, you know, one ear might be in a dead zone and the other might not be. So again, that would be different too. But in principle, this is a thing that like you could stick a microphone at different places and it would detect different volumes. And depending on how it was set up, some places you might actually detect zero volume. Yeah, no, it's very strange to experience in real life. Like, and similarly, well, so if the room is set up in a particular, if the room is specially designed, or if the room is set up in a particular way, then the bounces will occur, and then they will self-interfere with themselves, and you'll get dead zones. For example, there's a I think it's in Sedona. Sedona is north of Phoenix, or south of Phoenix. I don't know. It's somewhere in Arizona. I used to go there pretty frequently because I lived in Phoenix. So there's a like a timeshare resort thing that I have gone to in the past. And in their lobby is relatively poorly designed from a sound perspective. And the reason I say that is because they have a big dome on it, and that dome in their lobby is shapes the sound waves in the room so that if you stand in a particular spot, basically everything constructively interferes at that one spot. So if you stand there, you can hear somebody whispering on the other end of the room like they're right next to you because you get constructive interference from all of the reflections off of the walls. Forms a standing wave with a peak at that location. Poor design means that you can overhear financial conversations in the lobby. Not a great thing, but it happens. Like in real life, it actually happens. Anyway, so let's talk about Beats. So Beats is the resolution to the question, what if waves aren't exactly identical, meaning that they don't have the same frequency? What if they're just close? Well, so when that happens, you get an interesting phenomenon, especially when the frequencies just differ by a little bit. So let me draw you a picture of two speakers that are outputting, and this is going to be a dramatic picture, but they're going to output different frequencies, but they're going to, you know, be turned on at the same time and so on. So one of them maybe outputs a frequency like this. Another one outputs a long wavelength. So notice that at this point, you would have destructive interference at that point in space, and say at, I drew this poorly. God, this is hard to draw. There we go. And at this point, you would have constructive interference. So as time progresses and these waves move forward, these waves, they're traveling at the same speed, but at a later point in time, you will have a different set of phenomena because the waves will align in different ways because the frequencies are different. And so what we're going to imagine here in what follows, we're going to assume that the amplitudes, let me write this out as a set of assumptions. We're going to assume that the amplitudes, wave speed, because of the same wave, the same type of wave in the same medium, and direction are identical. And we're going to assume that the frequencies are different. Remember, frequency tells you how high pitched a sound is. So higher pitched sounds are going to be higher pitched waves, or are going to be higher frequency waves. So this is how we're going to analyze the system. We're going to ask what happens if you're at a place and you have two speakers that are traveling the same direction, traveling the same distance to get to you. We're cutting out all of the phase difference stuff, the total phase difference. The only, like they're turned on at the same time, they travel the same distance, they have the same initial phase. The only difference is that their frequencies differ. And so we can actually figure out what happens. We can do our best to understand what happens. Let's imagine that we are sitting at one place. What do we hear? Now, you may think that just like in the case of regular interference, like we just talked about, if you're sitting at one place, what you hear is going to depend on the location, right? If you're sitting at a place with constructive interference, you'll hear a loud sound. If you're sitting at a place with destructive interference, you'll hear a quiet sound. So what will happen if you just sit at a single place? Well, you might say it depends. And in this case, of course, it does depend, obviously. It depends on whether you're hearing a loud sound now or a loud sound later. But something else new happens. And that's that we get an oscillating effect of amplitude. We would hear an oscillating volume, quiet to loud and back and forth. And this is a result of interference effects, which forms beats. Now I'm going to play something for you that you might hate a lot. It's going to be headphone warning, I guess. So I'm going to share my screen on the other Zoom call. It's not Katy Perry, no, I promise. Need to mute. Oh no, this one's already muted. Okay, so right, I'm going to share my screen. Yes. I'm going to share this browser. All right, so what's on this browser is an adjustable, like you can adjust two waves, and both waves are going to play sounds out of the speakers of this computer. And actually, I need to make sure that that's true. Can you hear me? Can you hear me? Testing, testing, testing. Okay. It's going to play sound out of the speakers of this computer, and then it's going to go in through the microphone, and you guys are going to hear the combined sounds. So what I'm going to do is I'm going to start off with just having, we have a low pitch sound and a high pitch sound. And, you know, we're just going to add them together and see what happens. So headphone check. I'm going to turn it down and then turn it up as it gets too loud. Can you guys hear that all right? Okay, so what you probably hear is like a high pitch sound and a low pitch sound, right? And it just sounds kind of muddled. And if I played around at these frequencies, you could hear the difference. Like if I make one of them 100, roughly 100, I make one of them roughly 404, that's close enough. One of them is like 2 octaves higher if you're into music. The question though, is what happens if their frequencies get really close? So they still sound different. Oops. Okay, now you hear something completely different. Hopefully you hear it. Now you hear just like what sounds like one tone, just one tone, roughly 170-ish, 175 hertz. It's like a, what, 440 is an A, so this would be like a, oh, I can't do that math. 220 would also be an A, and so this would be like, no, I can't do that math. Involves logarithms. This would just be some tone. You just hear one tone, but it's changing in volume. And the reason is because if you look at this picture, let me see if I can zoom in. Initially, they start off roughly aligned, right? One of them, they have different wavelengths though. And so one of them will travel a different distance to get, or travel a different distance, travel for a different duration to get to a peak than the other. And so eventually what you end up with is I'm trying to find a good example of this. Okay, I can't find any good examples on this picture, but the point is sometimes you will see the peaks align, like roughly here. Okay, I can't point either. On the left, and then sometimes you'll see that the peaks anti-align, in which case you'll see, let me zoom out more. Oh no, that's why, it's because we can't see it. Let me increase the frequency a little bit, just so then it's more visible. Okay, still sounds the same, just a higher pitch. You still get oscillations, changes in volume, but now you can see that at very particular places, say at this line here, you have roughly a trough. This is on the right-hand side, roughly a trough lining up. Oh, cool, I can overlay them with a peak. And that's why you're hearing quiet. And then roughly half a beat later, you hear a loud sound. And if we brought these closer together, yeah, so I have to zoom out in order to make it actually visible. So this is the phenomenon that we see when we have two different waves of different frequencies. So let me share my screen and we can go back to the physics, or not the physics, but to the physics, the math part of the physics. Right. So we see this oscillating volume phenomenon. And so we can explain that using interference. So why does this happen? Let me move this up here again. So this happens for interference reasons, as I said. So we're going to make an assumption, just to make our calculations easier. We're going to suppose we are sitting at x equals 0. We're at some position x equals 0 for both speakers, and that's just because both sounds are playing out of the same speakers. So of course we're going to be the same distance from both of them. We'll just call that x equals 0. And let's say that both speakers started off with 0 phase constant, or that they start off with the same phase constant. So phi1 and phi2. This just makes things easier. We could do the same calculation with different positions, different phase constants. It won't change the phenomenon. It'll just change whether it starts off loud or starts off quiet. So the first wave, well, we're at x equals 0, and at time t, will look something like this. We're examining we're examining what the wave does, what the disturbance is at a particular point in space as it changes with time. So this would be a times cosine of 2 pi ft, or 2 pi f1 times t, plus phi1. And then we have the second wave at the same time, which is a cosine 2 pi f2t plus phi2. So far, so good. So we're going to set phi1 to be equal to phi2, and we're just going to get rid of these because we can just absorb those both into when the time starts. So if we can just start our stopwatch right when the phases of right when it's at its peak. So it starts off at cosine, so it's like cosine of 0. So if we just choose t judiciously, we can make that choice. Okay, so this makes things a lot easier. So then the total disturbance that we would see, it's a function of time. It would be f1 of 0 in t plus f2 of 0 in t. And so this would just be a times cosine of 2 pi f1t plus cosine of 2 pi f2t. Now this should look familiar because we did something very similar when we were first talking about interference. So again, we're going to use that same trig identity where we add two cosines with different arguments, and we get that the total disturbance, in this case it's the pressure wave, is 2 times a times cosine of 2 pi times f1 minus f2 divided by 2 times t times cosine of 2 pi f1 plus f2 over 2 times t. It's just the same cosine rule. And so what our wave function ends up looking like, or the resulting wave looks like as a function of time, is something like this. Where our wave is encapsulated by something that's called an envelope. And so you can see that the the frequency, there's two different frequencies involved here. There's the actual frequency of the oscillation. In this case, it's maybe like has a wavelength 3 times the size of this of one envelope width. And then there's the actual frequency of the amplitude shifting up and down. So for F1 being equal to, oh boy, this was a bad idea. I shouldn't have used F for the same thing. Okay, one sec. I'm going to fix this. Let's use capital F. There we go. Okay, problem resolved. There we go. Okay, so now the lowercase f means frequency. So for F1 is equal to F2 plus the change in frequency between the two, the difference in frequency, then and we also want that delta F small. So we want that the difference in when the difference in frequency is small, which is what delta F means, then we get that 2a times cosine of pi times delta F times t. This varies slowly. This is this term here, by the way. And in fact, it varies so slowly that we can hear it. Meaning it doesn't just sound like a sound, like a tone. It sounds like an actual oscillation. And so this term becomes something like a time-dependent amplitude. Just like on the standing wave, except now this is a standing wave in time rather than a standing wave in space. A beat really is just a standing wave in time rather than in space. It's just because we don't have reflections in time, that would be awfully confusing. We need two sources that are both traveling, and then they interfere at a given place, and you have differences in oscillations. And alternatively, or the alternate term, so that's that first term here. Just draw that arrow. The second term, cosine of, what is it? 2 pi f1 plus f2 over 2 times t. This is just a tone that we hear, which has a frequency that's the average of the frequencies. So we hear the average of the two frequencies. Which is kind of what we heard, right? We didn't hear like two different sounds. Well, okay, when the waves were close, we didn't hear two sounds. We heard like one tone and another tone. But when the two waves were close to each other, it just sounded like one tone, but with its volume changing. And that tone that we heard was actually the average of the two tones. If you could match it up with the average of two tones, and they would sound the same. So the question then is how do we find the time-dependent amplitude again? This is just trig. It's just trig stuff to go from here to here. And so this first term is a time-dependent amplitude. The second term is just the average of the frequency. Is an oscillation that has the wave. It's an oscillation that has frequency, which is the average of the two original frequencies. And so the beat frequency, and this is important, so I should write it down. The beat frequency, i.e. how often you hear those loud and quiet parts, is given by delta F. And the carrier wave frequency, this is the frequency that the beats are riding on, is given by the average of the two frequencies. And so, so let's just think about this just for a minute. Why is it that the beat frequency is given by delta F? Well, you might say, well, shouldn't it be given by delta F over 2? Because we need a 2 pi in front in order to get one full oscillation. But consider that we only hear intensity, not amplitude. So while it's true that the amplitude will become negative, we hear that exactly the same as if it were a positive amplitude. So so for every one full wavelength of our envelope, we hear 2 beats. Both the up and the down part of our envelope of this thing, we hear as 2 separate beats. We hear as woo woo. That would be one oscillation. So that's why we don't need the 2 pi there in order to get the frequency. So this just tells us that the frequency is just delta F. And you could plot this function, and you would see that it repeats itself. Or you could plot the square of this function, which would give us roughly the intensity. Remember, the intensity is like the amplitude squared. And you would see that there would be a peak there would be delta F peaks every 1 second. And so that's why the beat frequency is just the difference in frequencies. And so if we go back to our demonstration, actually, I think I can just play it from this machine. And then, yeah, I'll just play it from this machine and you should be able to hear it. If I put the frequencies very, very close to each other, so right now the frequencies are, I'm going to put them both at like, I have to do this with my finger, which is a lot harder. Okay, so right now it's 306 and 309. So if I play this, you should hear, so the difference between those frequencies is 3 hertz. So you should hear 3 beats per second. 1, 1000, 2, 1000, 3, 1000, 4, 1000. I mean, you get. Yeah, so it's roughly 3 beats per second. And, you know, it's kind of hard to do in your head, but that is what it is. We can set it to be exact. Let's see if I can get it to be exactly 1 second. Let me set it to be 308.2. So this should be precisely 1 second per loud, or per quiet region, per loud region. 1, 1000, 2, 1000, 3, 1000, 4, 1000, 5, 1000, 6, 1000. I mean, obviously I can't count exact seconds, but the point is this is exactly 1 second. You can get it a stopwatch and see. So that's how beats work. And that's why, by the way, if any of you play guitar, or I suppose this would work on any strings instrument, you can actually tune guitars this way. Actually, let me go grab a guitar really quick. Oh, wonderful. Vivian? Ollie or somebody threw up in the living room. Can you take care of it? I'm not sure. Yeah. And I just stepped in it. I can wash that off. Wonderful. It's by the blue chair, between the couch and the blue chair. Sorry about that, guys. I just stepped in cat throw up, which is fun. Right, so guitar. So this thing's horribly out of tune. It hasn't been played in a while. But what you can do is one way to tune your guitar is by making sure that one string is in tune and then tuning them relative to that. And the way you do that is just by playing 2 notes that are identical to each other. And if you hear a beat then that means that they're not in tune. So here I would play harmonics. So I don't know if you can hear this. Let me try a different string. Okay, let me actually get this thing out of tune so that it's more obvious. So can you guys hear how it's kind of like wiggling a little bit? So that's because they're not out of tune. And so this is like, because we can hear this, because we can hear that beat, we can actually very easily get very precise tuning this way. So I'm going to play them both and then adjust the tuning on the third string to get them into tune. And the slower the beating is, the more in tune they are. I think they're actually just about in tune now. Yeah, so now they're roughly in tune. Again, putting them out of tune. Tuning them. And now, if you want to be cool, you can play power chords. And so you can tune a guitar that way. And in fact, what's funny is that I first learned about this when I was taking guitar lessons as like a teenager or 12-year-old or whatever. I didn't know why this worked. I just knew that that's what my guitar teacher told me how it worked. I don't think he knew how it worked either, but it does work, and it works on this based on this principle of beat frequencies. It works because we can hear beats, we can hear differences in frequency a lot better if it's a difference in volume, as opposed to just listening to a sound and being like, oh, is that right? No, because we can't, unless you have perfect pitch, we can't really tell the difference between 308 and 309 hertz. We can tell when something is changing in volume slowly, and that's how we can tune our guitar. Right, so that's how beat frequencies work. And again, oh, just one more demonstration. I'm now going to play two notes that are very, very different. So those are not the same note. Here we go. So these notes are the same. A guitar resonates in a funny way, so they don't sound exactly right. That's why I used harmonics, because you can get better sound. But these notes tend to be the same. I mean, they have the same note name. So I can play two slightly different notes. They're too far away for us to actually hear that beat. Maybe you can hear it a little bit. Let me try playing. Sorry. You can hear a beat a little bit because the frequencies are close. But if I go a little bit higher up, now it just sounds muddled and you don't hear the beat anymore. And that's because the difference in frequency is too high. So this beat frequency phenomenon really only happens when the beat frequency is sufficiently small, something that we can hear, something out of the range of hearing. When the beat frequency is like less than 10 hertz, then you can actually detect that. Anything more than that, it starts to sound really, really muddled and mixed. All right. So this is all to say, now that we've talked about how we can handle sound interference in one dimension, we can now use the same type of calculations in higher dimensions. We just use the distances to compute the phase differences. And then we can determine where constructive and destructive interference occurs. So this is going back to that picture. If you have a source here and a source here, and we want to know whether there's destructive or constructive interference at that point x, you would just find distances, say x2 and x1, and then delta x would be x2 minus x1 or x1 minus x2, it doesn't matter which. And then if they were turned on at different times, you'd use that, and so on and so forth. So let me pull up just one more diagram or one more thing to show you. So this is a picture of what happens if you have different if you have two sources in two-dimensional space, right? So in this case, between them, it's just as if it were one-dimensional. So you see that we have oh, this is not the one. This is fine. So one thing that you can see is that you have destructive interference on the black lines and constructive interference on the red lines. And the reason that happens is because if you look at the black circles, which are the peaks, and the gray circles, which are the troughs, they perfectly align along the red lines, and they perfectly, like the peaks align with the troughs along the black lines. And so you would always have destructive interference there. And this is a result of distance. Now we can change the wavelength if we wanted to, but I'm not sure how much that would help us. The point is that the pattern of destructive and constructive interference occurs in different ways. And in fact, if we get this far today, we will get to that same sort of phenomenon occurring with light. Let me share back here. So, and just one more thing before we continue. And this is mentioned in the lecture notes. So for wave energy, so you might ask, well, okay, if there's dead zones, where does the energy go in the constructive interference, constructive destructive interference? In principle, it should go somewhere, right? Like energy is conserved. And so you might say, well, would it be possible that you could have two waves, two sources that constructively interfere everywhere in 2 dimensions or 3 dimensions? Well, by energy conservation, of course not. And in fact, this is just mathematically true. For every one point that has destructive interference, you'll get a point where you'll get the appropriate number of points that you need of locations that have constructive interference. And this works out so that you always have the same amount of energy, even though the energy is just distributed in a lumpy way. You have some energy, more energy here where there's constructive interference, and then no energy in the lower place. Yeah, for these x values, it would just be, you would just use the Pythagorean theorem. Yeah, precisely that. So for example, for 2 waves, for every region that has for every destructive interference region, you would also have one constructive interference region. And that's just how it would work out. That will always happen. So if you ever have a dead spot in a room, try to see if you can find the loud spot, because it should be there, right? Otherwise, energy wouldn't be conserved, and that would be kind of strange. Right, so we're going to change gears basically completely now. We're still talking about waves, but we're going to talk about a different kind of wave, and that's light. So this is section 3. So let's try to understand what light is. So unfortunately, you guys don't really have the tools to answer that question. You'll learn about it in more detail in 9C, but I can at least give you some background. So in the 1800s, I want to say it was like the 1850s or the 1870s or something. So light isn't photons. Photons are light, but anyway, sometime in the mid 1800s, an Irish fellow, Scottish fellow, somewhere from the British Isles, a fellow named James Clerk Maxwell, or pronounced locally James Clerk Maxwell, showed that electromagnetic waves, and these are waves that are just formed by oscillating electric and magnetic fields, satisfy a wave equation. Come on, scroll, please. James Clerk Maxwell. He showed that EM waves satisfy a wave equation that's like it's not quite like this because these waves are 3-dimensional waves, but it looks something like this. df dx squared equals epsilon naught mu naught d squared f dt squared. It looks something like that. And then here's where the magic happened. If we let v be equal to 1 divided by the square root of epsilon naught mu naught, and by the way, these epsilon naught and mu naught, these are just physical constants. They're called the permittivity and permeability of free space, and you'll learn about them in 9C. Then this just becomes a wave speed. And the units work out that this does have units of speed. Then this is just a wave equation with speed v. The wave has speed, and these are physical constants that you can just plug in numbers for. C, we call it lowercase c. I think that was an Einstein thing. This is equal to 1 over the square root of epsilon naught mu naught. That's just the speed that the wave travels at. And this electromagnetic wave happens to travel at 3 × 10⁸ meters per second. which Maxwell also observed happened to be the measured result for the speed of light. So he concluded light, whatever it is, travels at the same speed as this electromagnetic waves. So that means that they must be the same thing. So he concluded that electromagnetic waves are light. And he was right. Like that is just true. So just like any wave, these waves have features. So things like polarization, the medium, what they're displacing, and so on. So we should talk about those. So, and light is very strange in a few of these regards. So light can travel through any medium, or can travel through lots of media. I.e., it travels through glass just fine, it travels through water just fine, but it can also travel through no medium at all, which is surprising because up until now, every wave that we've talked about has had to have a medium through which it travels. A displacement wave on a string travels in the medium of the string. A sound wave travels through the air or the water or whatever. A compression wave on a slinky travels through the slinky. An ocean wave travels through the ocean. A light wave can travel through nothing at all, through the vacuum of space. And we know this because there's nothing between the sun and the earth, and yet light gets from the sun to the earth, so it has to travel. This is actually a result of an experiment that took place in the late 1800s called the Michelson-Morley experiment. They determined that there is no medium through which light travels, which basically paved the way for special relativity, Einstein's theory of special relativity. So that's one way that light waves are strange. Another way, you might ask, what is the disturbance? Like, so on a string, the disturbance is vertical motion of the string. In a sound wave, the disturbance is pressure differential from ambient. In a light wave, it's a little bit different. The waving things are the electric and magnetic fields that are changing with time. Now, these are vectors. And so vectors have a direction. You guys know this, I think. I think this is covered in 21D. So maybe you guys have already covered this. These vectors have direction. And so they have a magnitude. So you can imagine that a vector that points up and then points up again and then points down and then is 0 and then points down and then like that, that is a thing waving. It's just not something that you can physically grab onto, but it's still something. It changes from having 0 value, these electric fields, or the electric field, 0 value at some point, to not 0 and then back again. And so it oscillates just like the position on a string, or just like the height of a string. It oscillates up and down. In this case, it's just some abstract thing called the electromagnetic field. Now, if this doesn't make sense to you, that's fine. You'll learn about this in 9C. But the point is there is this thing called the electromagnetic field, or the electric and the magnetic fields, that change with time, and they propagate like a wave. The last thing is polarization. So the polarization of a light wave, again, you might say, well, how do we figure out what direction the thing is oscillating if it's not like a physical thing oscillating? Well, just like sound, there wasn't a physical thing moving in sound. It was more like there was pressure differentials. So we were asking, what direction does the pressure change in? And it changes in the same direction as the wave. In this case, we ask, what direction does the electric field change in? And so we look at the direction of the electric field, and the electric field is a vector, so it has a direction. And we call that the polarization. While it's oscillating, of course. So it turns out that, and I'm going to try to draw this, this is going to be terrible, I'm sorry. It turns out that if you have a wave traveling like this way, your electric field's going to oscillate like this. Oh God, this is so bad. There's a picture in the canvas that that's a better picture of this. And then your magnetic field. This is so bad. Okay. Let me just screen share. I just want to show you this picture because it's a little bit easier to see. I've drawn this in the past, but it's always really bad. Yeah, here it is. So the red in this case would be like the electric field, and the blue would be the magnetic field. So just by convention, we choose to use the electric field for the polarization. So the direction, in this case, it's kind of like up and down. And the direction is the direction of the disturbance is the direction that the electric field is oscillating. And that in particular is always perpendicular to the direction of motion. This would represent a transverse wave. The electric field cannot oscillate in the direction of motion of the wave. It always is perpendicular. And again, actually, you won't learn that in 9C, but if you go further in physics, you will learn why that has to be the case. But that is just a phenomenon that happens. So one last thing that we can ask about is, well, we did this with sound. We can ask how we perceive it. How do we perceive light? Well, we use our eyes. We detect the intensity, just like for sound. And again, it follows a logarithmic rule. So like doubling the intensity doesn't double the brightness. And the way that, just like how we detect different frequencies of sound, or different wavelengths of sound, those two things are kind of interchangeable. By pitch, higher frequencies, i.e. shorter wavelengths, are higher pitch, they sound higher. We can do the same thing with light. We're using our eyes now. So here, frequency is the thing that determines color. And this is only true in the visible range, of course, because there's a whole swath of electromagnetic waves, of light waves that we can't see, just like how there's a whole swath of sound waves we can't hear. For example, sound can be heard roughly by the human ear from about 20 hertz to 20,000 hertz. Anything more than that, we can't perceive it. Anything lower than that, we can't perceive it. We just won't, and if it's significantly higher or significantly lower, we just won't even know it's there. Similarly, for light waves, frequency, and I actually typically talk about wavelength when it comes to light waves because it's more familiar to me. But when we talk about light waves, there is a lower wavelength, which corresponds to a higher frequency. Those correspond to a certain color. In particular, so actually, let me, so the visible range of wavelengths, and you can work out the frequency using the speed of light for yourself. The visible range of wavelengths is about 400 nanometers, so very, very tiny, which is violet or blue, to about 700 nanometers, which is red. And everything in the middle, all colors in the middle, fall between 400 and 700 nanometers. This is the distance between peaks of the electric field. That's a very small range, right? Like you could have wavelengths that are like 2 nanometers, or you could have wavelengths that are like 6 meters, right? Remember, nanometers are a billionth of a meter. So what about everything else outside? Well, that forms the rest of the EM spectrum. So if we have higher frequency, remember, frequency is the inverse, effectively the inverse of wavelength, because wavelength times frequency is speed, and speed is constant. Higher frequency, which is shorter wavelength, these make up the higher frequency parts of the electromagnetic spectrum. These are things like UV light, X-rays, gamma rays, all of those things. Those are all types of electromagnetic radiation. They're just outside of the range that we can see them. Just like how very high-pitched sounds are outside the range that we can hear them. There's also lower frequency, which are longer wavelength. These are things like infrared. We can't see infrared, or even microwaves, or radio waves. Now, higher frequency, lower wavelength electromagnetic waves are relatively hard to generate in a controlled way. Like we can generate X-rays relatively easily, but they're not nearly as easy to control. And the reason for that is because they pass through a lot of stuff, so it's hard to like get them going in a cavity and then like output them in a certain direction. UV light we can make, but again, it's harder to make. Visible light is relatively easy to make. We use light bulbs. We have plenty of LEDs that can do this. You can just heat something up and you get visible light. Lower frequency waves are also relatively easy to make, and that's basically the difficulty in making these frequencies, these wavelengths, goes up with frequency, or down or up with lower wavelength. I.e., the higher the frequency, the harder it is to make. And that's just because they have more energy, but that's neither here nor there. So lower frequencies are relatively easy to make. For example, we can make IR flashlights. Those have existed for a long time. In fact, most of the old light bulbs that you've seen, like the ones that get really, really hot, the halogen light bulbs, those emit most of their electromagnetic waves in the form of infrared. The reason they get so hot, infrared heats up things very easily. It gets absorbed easily by material, and that absorption increases the energy of the system, which makes it hotter. So infrared gets absorbed really easily, so it heats things up, and that's why those old halogen light bulbs get really, really hot, so hot that it can burn you. It just happens to be that they also emit some visible light that helps us see, so we dealt with that for a long time. Now, modern LEDs don't need to emit nearly as much total energy because they're not emitting any infrared. If you go even lower, you get microwaves. These are things that have a wavelength on the order of 10 centimeters. These are all, again, absorbed by particular materials, in particular, about 11 centimeter wavelengths, which is a type of microwave. That's absorbed by water. It's absorbed very well by water. So if you generate that kind of wave in a cavity, and you put something that has a lot of water in that cavity, that water will absorb the energy from the light wave, from the EM wave. And that's how a microwave works. A microwave works by producing microwaves and then having them be absorbed by things that have water. And food happens to have lots of water. You'll find that wet things tend to heat up a lot faster in a microwave than dry things. You can go even further. You can go even to longer wavelengths, to even lower frequencies, to radio waves. Radio waves are even lower, and in fact, you can almost treat them like sound, because not because they change pressure or anything, but they have wavelengths like that of sound, like on the order of meters. And so they can just bounce off of like pieces of metal, just like sound can. And so you can focus them and direct them and like listen for them by using like radar dishes. Radar stands for, I should know this. Well, the R in radar stands for radio. I should know what radar stands for. Radio something, navigation and ranging, I think, basically to figure out where things are. And they use radar for that because it's easy to control. But so the whole spectrum of wavelengths are relevant to everyday life, right? Higher wavelength or higher frequency, lower wavelengths are dangerous, turns out, like UVA, UVB, UVC, those can be damaging to your skin. X-rays can give you cancer, gamma rays will give you cancer, and so on. So that's the basic gist of light, but light is a lot more complicated than that. Yeah, or green monster powers, yeah. There was a guy in Russia, or I guess it was the USSR at the time, I think in the late 80s, who stuck his hand accidentally, no, his face accidentally, in the path of a particle accelerator, of an atom smasher. And it was only on for a moment, but if you looked at the X-rays, there's just a line through his face of just destroyed tissue. Gamma rays would kind of do that. So don't mess around with gamma rays. It's an interesting story. I'd suggest you reading up on it. Anyway, so what we're about to talk about, this thing called Huygens Principle, applies to light, but it also applies to actually any three-dimensional wave, but it's most useful for understanding how light works. So Huygens Principle, and I'm going to copy this word for word because I want to get it right, is basically a statement about how waves propagate in 3 dimensions. So it is the statement that every wave, every 3D wave, propagates by having every point on a wavefront being like a line or a surface formed by all of the peaks or all of the troughs or something. Every point on a wavefront act as an independent generator of another spherical wave. So remember that, like, if you just have like a light bulb, it's going to emit waves in a spherical direction. 3-dimensional waves generally propagate as spherical waves. They emit just like shells of peaks, right? So the point is that every wave propagates by having a point, by having every point every point on a wavefront act as an independent generator of another spherical wave. And the observed wave is just the consequence of the interference of all of those waves. So this seems strange, but it's actually not too hard to understand why once you see a picture. So I'm going to do my best to draw a picture. So let's say that we have a wavefront that looks like this, right? It's coming from some source, maybe over here or something. So I'm just going to draw a bunch of points on this wave. Actually, you know what? Let me just show you a picture because it'll be easier. Here we go. So imagine that this dotted red line is a wavefront, and then we're going to just keep adding more and more points. So imagine that this is just a plane wave. A plane wave is just a wave that's traveled for so far that it's roughly flat. So then, well, if we just treat 3 of those points on that plane wave as sources, then you get this kind of lumpy 3 new wavefronts. With 5-point sources, you get something that's slightly more flat. With 9-point sources, you get something that's even flatter. And once you make it so that every point on that wavefront, there'd be an infinite number of them, produce their own wavefront, you get the next wavefront is the place where all of those waves constructively interfere to produce another wavefront. And then that wavefront will produce another wavefront, and so on. And so the wave propagates forward. The wave doesn't propagate backward, basically, because of interference from previous wavefronts and the wave itself. So you might think that the waves in the back of the 9-point source would constructively interfere and would travel in both directions, but also the wavefronts from the previous thing would destructively interfere with that. So that's why you don't get waves traveling in both directions. And so you can do this with really any sort of phenomenon. I'm not going to draw that. And so in fact, it turns out that there's this phenomenon called diffraction, which basically is a result of Huygens Principle. So Huygens Principle just says that each point on the wavefront behaves like a spherical wave generator. And those points on the wavefront, well, that's why waves can bend around obstacles. So even though an obstacle, like this barrier here, might block some of the wavefronts, that doesn't stop the wavefronts that weren't blocked from emitting in a spherical way. And so that's how you end up with, at the bottom of this diagram on the right, that's how you end up with waves bending around corners, because those waves are going to emit their spherical wavefront, and then that will produce a new wavefront, which will emit its own wavefronts, and so on. And so you'll just get waves that propagate around corners. Now, it is the case that waves also go around corners from bouncing off of things, like from bouncing off of walls and so on. But diffraction plays a major role, this phenomenon of diffraction. And by the way, diffraction is the notion that waves can bend around barriers using, or as a result of Huygens Principle. This notion of diffraction plays a key role in how waves can go around barriers. Now, just as a side note, this notion of diffraction is actually almost associated with this notion of interference. And you'll often hear when somebody's really talking about some sort of fancy interference, they're actually also talking about, or they might be talking about diffraction or vice versa. Sometimes that just happens. And the reason this happens is because this notion this Huygens Principle and this notion of diffraction is so intimately tied with how a wave interferes with itself that you'll see interference and diffraction just used almost interchangeably. So I think that I will end it there. I do suggest you take a look at the diagrams and do some reading on diffraction. It's kind of hard to get your head around. Actually, no, never mind. You know what? And maybe I would suggest like Googling for diffraction GIFs just to get an idea as to what this kind of thing looks like, so you can see it happening in real time, like going around barriers. No, so diffraction just always happens. That's a good question. But so actually, I'm going to end lecture here. But I will be, so we're going to end a few minutes early, and I will just take questions. So I'm going to end the recording here.